Well, let's get started on the next problem. This is going to be LeetCode problem number 11, container with most water. You are given an integer array, height of length n. There are n vertical lines drawn such that the two endpoints of the ith line are I0 and I height I. Two endpoints. Okay, yeah. Find two lines that together with the x-axis form a container such that the container contains the most water. Return the maximum amount of water that a container can store, and note that you cannot slant the container. Okay. So, well, the area between the two will be min of, and we'll call this I and j, between any two arbitrary lines. Line heights I and j will be min of I and j, or we can say height of I and height of j between any two ij will be the height, the minimum height between them, multiplied by j minus I, which will be the difference between them in terms of the x-axis. So, for example, here we have 7 and 8, I think, is the solution. So the minimum is 7 times 0, 1, and 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 minus 1 is 7, so 7 times 7 is 49. We are given that the number of elements within our array, or number of inputs that we could possibly have, is between 2 and 10 to the 5. Okay. Let's try to think of a solution. A brute force solution would be for each element in height, for each element beyond the current, calculate the area and store a running maximum, and then return the maximum. This would be O of n squared time, where actually, no, this would be n cubed time, where n is the number of heights in our array. And the reason why is because this will create an O of n this will create an O of n runtime for each element in height, because we're running a linear scan. And for each element beyond the current, that means that we will be doing n minus 1 plus n minus 2 plus all the way to 1, which I believe is equivalent to n minus 1 over 2, which is equivalent to O of n squared. And since this is this is happening on, well, no, not quite actually. Because yes, this ultimately does run in O of n squared time. We aren't running this O of n squared algorithm each time. Rather, we are only running at most O of n, right? So this would be O of n minus 1 then O of n minus 2, right? So ultimately, this results in an O of n squared runtime rather than an O of n cubed runtime. But given that our input array is 10 to the 5, that seems like a little bit slow. Let me think. Sorry, had to step away for a bit there. Anyways, let's see. Well, let's run down the list of what can we do to improve the potential runtime. Sorting? No. Primarily because that would mess up the input, and we need the input to stay in the same order. So this doesn't feel like a sorting solution. What else could we potentially do? Well, there's no... The problem, I guess, is that there's no ordering in the inherent height set. That would allow us to greedily take swing at the problem. We don't know for sure that we can check the next one. Sure, right? We can start with the pointer at the end and the pointer at the beginning. And sure, we can check that the next one, whether or not it will be bigger. But there's a chance that one of these ends isn't, like, for example, would we want to shrink down here? Well, probably not. But there's a larger element here, right? And then we have to compare, like, oh, is this area greater than this area? The height is limited to 10 to the 4. Ten to the 4. Still a decent amount. I think it makes sense that O of n is probably possible given the array, or given the size of inputs possible. O of log n probably not, without some ordering, which this really doesn't have a lot of ordering. So I don't think O of log n is possible. But I think that O of n is probably possible given the size constraint of 10 to the 5. Well, if we start at each end, we can calculate the input here at this layer. We can calculate the area at this layer. We can compare it to this layer, but again, that greedy approach doesn't really take us anywhere, does it? I'm sort of thinking of whether or not there's any input that we can get between here and here that would make it more reasonable, that would validate sort of, or not validate, I guess the correct word is that I'm not sure if where is the duplicate work that we're doing here in this case. So let's say, for example, our brute force, we do this, and then we check this, and that, and that, and so on and so forth. Then we check here, and then here. Well, is it possible that we hash something? I guess the idea is that, okay, so we can do this with the O of n squared runtime, but we also throw in an element of hashing, maybe. Throwing items into a hash map. Particularly, I guess, the elements and sort of their heights. So maybe even a set, but... And then the idea is that we want to essentially check at this point whether or not there is an element given the height within here that given the height would actually beat this. That seems interesting. Alright, so if we have 8 here and 7 here. Well, we would need an 8 here. Right? So this is 8 times, or this is 7 times 7. So 7 times 7. The only thing that can beat that is maybe not even an 8 times 6, right? Which would be here. So because nothing else can beat, so 1, 8, 8, 6, 2, 5, 4, 8, 3, 7. Suppose we're at 8 and 7, and we've just calculated that the area is min of 8 and 7 times, this is 8 minus 1, equals 49. And the largest we would need is, or the next largest we could get is we would have to change min and the left side and the right side, right? And we would have to change it such that we achieve a number greater than or equal to 49. But is that even possible, right? If we find a 9 here, it doesn't matter that it's a 9 because it's 8 times 6 at that point, which is 48. So we should move the smaller number inwards, maybe? So if we did that, we had 1 and 7. Let's see, 1, it would start with 1 times, or it would be 7, no, 1 times 8 is equal to 8. Then we move the small one inwards, so that would be, so this would be a new max. Then we'd have 7 times 7, which is 49, which is a new max. Well, now this 7 is smaller, so we move it there, so now it's 3 times 6, which is 18. And this is still smaller, so we'd now move to 8 times 8, or not 8 times 8, this would be 8 times 5, which is 40, which is here. Then we move it down to, well, here we could probably move. Should we move both of them in this case? We move both if they are equal. That's a good question. Let's suppose we did. So now we have 6 and 4, which is 4 times 4, which is 16, and so on and so forth. This would be O of n runtime, but would it work? I guess the idea is, would it consistently work such that we always find the maximum in that case? We could try that. So var left is equal to 0, var right is equal to height size minus 1, while left is less than right. We should say var max is equal to we can start it at 0, it doesn't really matter. Length of the array is at minimum 2, so we should be fine there. Val current area is equal to min of height at left, height at right, times right minus left. If max is, or current area is greater than max, max is equal to current area. And then we can say if height of left is less than height of right, then left minus or plus plus, otherwise right minus minus, and then we just return max. I think this should compile. And this gives us the correct one for this example. And it gives us the correct one for, or at least it should give us the correct one for this example as well. But I'm just not sure as to whether or not this solution is valid for all cases. I don't feel like I have a compelling enough sort of logic. I don't have a compelling enough proof that this would work for more items. Because the idea is that we can't just do like a greedy thing to say like, oh, if this bar is less than the next bar, then we move it. Because the problem with that is that we could have a situation like this where the bar is lower and then higher there, and maybe the actual solution is behind that. So we can't really check that, right? So we kind of just have to shift our pointers left and right, or inwards, until we find a good solution. And I guess the idea is maybe that at some point within here, we sort of hit a point where, no, we probably won't hit a point because of the maximum height that could be possible. I don't think that there's any reason to believe that there's any like minimum height at which we can terminate this. I think we just have to check all of them, starting at the end and then shrinking inwards and checking. And the reason I guess why we shrink the lesser of the two is because, well, we want the area to increase as much as possible. And in that case, we know that we have a maximum here, and maximum here, minimum here. It makes no sense to decrease our maximum, our potential maximum, for something else. At least that's what I think. But I'm really not sure as to whether or not this is the correct solution. I mean, I guess we could toss it in and we can give it a shot to see. Um, hmm. But I'm really struggling to think of like whether or not there's a really deeper proof behind like, oh, we just shift it so that the lesser of the two goes inwards, and yeah. I have been told by a friend that it's like a two pointers problem. It's like we were talking about this a long time ago. Actually, I think it's been 1 or 2 weeks now. Um, but I don't know much beyond that. Um, hmm. Let me think about it a little bit more, and maybe I can think of some better way to prove this. But I don't think that there's any way that we can sort of know sort of what lies in between the two without checking them ourselves. Obviously, we don't want to just be moving them inwards until they cross. Um, and the reason why we don't want to be just moving them inwards until they cross is because if both of these pillars are still good, then moving them inwards both to smaller pillars, even though we don't necessarily know that, um, is incorrect. Um, hmm. One thing that I'm also just like that's coming out of my mind. I'm not sure if this is a good idea or a terrible idea. I'm leaning on terrible idea for now. Is like if we establish a new maximum, then we sort of expand it out until, uh, or we sort of expand it to see if we can get any more. Well, if we expand it to try to get any more, well, we've already explored most of those cases, right? We just haven't explored them with the addition of we haven't explored them with the addition of our new maximum. And in that case, because we're shrinking it smaller, our new maximum would be smaller in the x-axis rather than anywhere else. So, hmm, just thinking whether or not this, man, I really wish that I had a stronger proof for this, but I really don't. I'm gonna probably just toss it through a submission now just to really get a counterexample if it exists or if this passes. But in any case, I'm going to have to check the discussion tab because I just where is the intuition? There's got to be some intuition to this solution if it passes, of course. But we moved the smaller one. I guess to a certain extent that's still like the greedy way to do it, right? Because we keep our maximum, so we're kind of saying, okay, so this is the current theoretical maximum. We compare against this, right? Um, and if we find a better maximum, then we say, okay, then we compare against that instead. Um, hmm. Yeah, I do wonder if there's like a situation where once we find a new maximum height, we push the other side we hit a until we hit a point where it doesn't make sense. I'm not too sure. Well, let's throw it through a submit and let's try to see if we can get a counterexample. Or I guess it just works, but okay, let's just go to the discussion tab to see why. Simple and clear proof and explanation. The widest container is a good candidate because of its width. The water level is the height of the smaller one, yeah. All the other containers are less wide and thus would need a higher level water to hold more water. Yes. The smaller the smaller one of first and last lines don't support a higher water level and thus can be safely removed from further consideration. I don't get it. I'm sorry, but I don't get it. What? Like, maybe this'll click like after I spend some more time, but like something about this just doesn't seem very satisfying to me. It's like, sure, it makes sense that we move the smaller one because we have a larger sort of, um, a larger maximum with the larger side. But how does this guarantee, like, how does this guarantee this? I don't know. Maybe I'll just write out like a full greedy proof for this. Maybe it'll make sense like if I actually write out the proof for this. Um, but uh, oh gosh, I really hope that this doesn't get asked in an interview before I like fully understand like the rationale behind this. Maybe there's some other better explanation here with proof and explanation. General idea to find some max go through all cases. Yes. I smart just cut off the useless cases. Yeah. Okay, and then every time we move after the two, all the maximum cases have been scanned. Given A1, A2, A3 as an input array, AN. Okay, yeah. Assume that A10 and A20 are the maximum. We need to prove that A20 can be reached by the left pointer, and during the time the left pointer stays at A10, A20 can be reached by the right container. That is to say, the core problem to prove is that when the left pointer is at A20, or A10, and the right pointer is at A21, the next move must be the right pointer to A20. Since we are always moving the pointer with the smaller value, i.e. if A10 is greater than A21, then we should move we hope. Why? Because if that holds, then the area of A10 and A20, if that is so, must be less than the area of A20 and A21. So if we have a left side that is larger than the right side, then we move the right side inwards. Because if we move the right side inwards, or because if we moved it the other way, why if A10? Why if left side greater than right side? Because if that doesn't hold, then the area must be less than our current area. And why is that? If this is smaller than this, and we move the other side, then we are decreasing our maximum to some value between 0 and our current minimum. Okay, so if we move the maximum, the greater of the two, then our area, of course, our x-axis will for sure decrease by 1, and our area is limited to some number between... No, our area is not limited. Is it? It is because we have a smaller number. So our total area will be guaranteed -1 on the x-axis. And because of our minimum on the right-hand side, and we decided to shift the maximum, then that area will be guaranteed to be between 0 and our minimum. Because even if we have a larger number, it doesn't matter because our minimum is still the smaller of the two. Conversely, if we decide to move the smaller number, then our area still will be less on the x-axis. However, our theoretical maximum is between 0 and our greater of the two, not 0 and our lesser of the two. Okay. So I think that's part of it. I think that would be considered like maybe like the greedy choice property. Then what happens to the other part, which is our subproblems? I forgot what the actual term of it is. But basically the induction step of this. Well, if there exists a larger area in between, well, how do we guarantee that we will actually reach that condition, right? Well, we exhaust all the cases by going through. I guess we just exhaust all cases because we just go through all the possible values in this case, but that's not a very satisfying proof to me. It does make sense, but yeah, I get the why move the smaller part now. That actually does make a lot of sense. But I'm not sure about the exhaustive part of this. Of course, it does make sense in retrospect because um, we kind of just go through all of them. And if a larger one exists, then we should move to that based on moving the smaller edges. Um, hmm. Because if a larger area exists than the one that we currently have, then first of all, because we're starting at the edges, right, with the width, we're maximizing the width. So we don't care about the width, we don't care about the possibilities, including the width, because we've already maximized the width in that case. So beyond that, we don't really care much about the width. We kind of just care about finding, I guess, like sort of the earliest highest. Or well, we don't really care about the earliest highest. We just sort of check all the highest ones, all the possible highest combinations essentially, until we can't. I guess that's a little bit more reasonable, but still, this is not a very satisfying conclusion in my opinion. Um, I don't know. Maybe I'll just write out the proof manually off camera or something. But in any case, that is LeetCode number 11, container with most water. I hope you learned something, and I'll see you for the next problem.